Hey, welcome. Take a moment and settle in. Curiosity brought you here, and if you follow it, it tends to take you further than you expect. Subscribe if you enjoy that journey. Now, let's start at the beginning. You begin by letting your mind settle into a quiet space, where the distance between you and the cosmos feels gentle rather than vast. You let your attention move toward a simple question. Why do neutron stars and black holes so often appear side by side in the language of astronomy? You notice that the question itself comes from how both objects form from the collapse of massive stars. You sense how gravity shapes their behavior. You start to see that the comparison is not about mystery but about the physics that becomes visible when matter is pushed to its limits. Here, you let your awareness settle on what the evidence shows. Neutron stars and black holes both arise from the dramatic ending of massive stars, but they represent different outcomes shaped by mass and internal pressure. You picture a star far heavier than the sun reaching the end of its nuclear fuel. With no energy left to resist gravity, its core collapses inward. You follow this collapse not as an imagined drama but as a process confirmed through supernova observations, neutrino detections, and models built from well-tested physics. You rest in the idea that these outcomes are firmly rooted in measurement. You allow your thoughts to move gently to the key difference that scientists observe. A neutron star forms when the pressure inside the collapsing core becomes so intense that electrons and protons merge into neutrons. The collapse stops because neutron degeneracy pressure resists further compression. This is not a guess but a consequence of quantum mechanics and nuclear physics confirmed in laboratories and particle experiments. You recognize that the object left behind is extremely dense, typically no more than about 20 kilometers across. Its mass, though, may be more than the sun's. You sense how such density allows strong gravity without crossing into the realm of a black hole. You then bring your attention to what makes a black hole different. If the collapsing core has enough mass, even neutron degeneracy pressure cannot stop gravity. The matter continues to contract until it reaches a point where the escape velocity exceeds the speed of light. This threshold forms what is known as the event horizon. You understand that this concept is not speculation but a solution to Einstein's equations of general relativity, supported by indirect observations such as gravitational waves, stellar orbits near compact objects, and the detailed image of a supermassive black hole surrounding light captured by the Event Horizon Telescope. As you rest with these ideas, you notice that both neutron stars and black holes emerge from similar beginnings but diverge because of precise physical limits. The deciding factor is mass. Below a certain mass, the collapse halts and a neutron star forms. Above that limit, gravity continues to compress the matter into a black hole. This limit is supported by observational data from pulsar timing, X-ray measurements, and gravitational wave detections that reveal the masses of compact objects. You sense that these observations give clear boundaries rather than hidden identities, helping you understand that the two objects are distinct outcomes of the same cosmic process. You allow yourself to explore why people sometimes feel that neutron stars might be masking a deeper identity. The extreme density, the small size, and the intense gravity can make them seem close to black holes in popular imagination. Yet, the scientific picture offers clear, measurable differences. Neutron stars emit light, pulses, and thermal radiation. They spin in predictable ways that can be measured with extraordinary precision. Their surfaces and magnetic fields leave observable signatures across the electromagnetic spectrum. Black holes, in contrast, lack a surface and emit no light of their own. You begin to see how distinct the evidence makes them. With this understanding, you let your attention rest on the nature of scientific comparison itself. The question of whether a neutron star could actually be a black hole in disguise becomes clearer when you consider how observation works. Astronomers measure timing patterns, gravitational interactions, and spectral lines. Each measurement offers a piece of information that fits into established physics. Neutron stars fall into a specific range of masses and radii, while black holes inhabit a different regime. The consistency of these measurements across decades supports a coherent picture. You begin to appreciate how reliable these distinctions become when they arise from repeatable evidence. You notice that answering the question does not require speculation but careful attention to what has already been observed. The strongest support comes from systems where neutron stars interact with companion stars. In these cases, astronomers can determine mass through orbital motion and see that the values fall below the threshold required for black holes. Pulsars provide further confirmation, allowing measurements of rotation rates and magnetic field strengths that do not match what would be expected from a black hole. Each of these observations adds clarity, guiding you toward a calm confidence grounded in data rather than assumptions. You let the idea settle that the comparison between neutron stars and black holes persists not because the two are easily confused, but because they both push physical laws to extremes. When matter is compressed to such densities, your intuition may feel stretched, yet the evidence remains consistent. A neutron star behaves according to the properties of nuclear matter and quantum mechanics. A black hole behaves according to the curvature of spacetime described by general relativity. These two frameworks meet only at the boundary where one object transitions into the other, and the observations show where that line is drawn. You begin to feel how the question, when viewed gently, opens a space for understanding the relationship between gravity and matter. Instead of hiding identities, the universe displays a range of outcomes that follow predictable rules. The mass of a collapsing core determines whether pressures inside the matter can resist further contraction. This balance is measurable, not mysterious. It helps you sense that neutron stars and black holes are complementary parts of cosmic evolution, each revealing different aspects of physics under extreme conditions. As you settle into this clarity, you hold the idea that learning about one helps illuminate the other. With this understanding in place, you allow yourself to return to the original question with a softer perspective. You see that the comparison arises naturally because both objects emerge from the same kind of stellar collapse, yet the physics that follows is shaped by well-measured limits. You consider how scientists observe neutron stars through their precise pulses, thermal emission, and gravitational influence, each measurement reinforcing their identity as dense but stable remnants. You also consider how black holes reveal themselves through the motion of nearby matter and through the gravitational waves produced when they merge. The distinctions are not subtle traces but clear, repeatable signatures. You feel how comforting it is to rely on the consistency of these observations. They show that the universe, even at its most extreme, follows rules that can be studied, tested, and understood. As your mind settles into this steady picture, you sense how these objects mark neighboring regions of physics, inviting you to explore how matter and gravity behave when pushed even closer to their limits. You rest in this understanding. You let your thoughts drift toward a massive star nearing the end of its long life. You picture it not as a dramatic object, but as a stable sphere of hot plasma held together by gravity and supported by the steady outward pressure of fusion. For millions of years, its core has fused hydrogen into helium, releasing energy that counters the inward pull of gravity. You follow this balance as a calm, predictable cycle supported by well-understood physics. In the quiet of your mind, you focus on the idea that every change ahead begins with the gradual depletion of the star's hydrogen supply, a process confirmed through observations of stellar spectra and models tested across different ages of stars. As hydrogen runs low, the core contracts slightly, becoming hotter and denser. This increased temperature ignites helium fusion, forming carbon and oxygen. You understand this not as a sudden shift but as a natural consequence of how nuclear reactions behave under higher pressure. Stars with masses greater than 8 times that of the Sun move through additional fusion stages, each igniting when the core becomes dense enough. Helium becomes carbon, carbon becomes neon, neon becomes oxygen, and oxygen becomes silicon. Each step is well established through nuclear physics and supported by studying supergiant stars in various stages of evolution. You can sense how these processes gradually build layers inside the star, somewhat like the layers of an onion, though you remember this is simply a structural analogy used to describe how elements arrange themselves by weight. At the center of these layers, silicon fusion produces iron. Here, you pause, letting the importance of this step settle. Iron is different from the elements that came before it because fusing iron does not release energy. The star has reached a point where nuclear reactions cannot provide the pressure needed to counter gravity. This fact is grounded in measurable nuclear binding energies and is one of the clearest, most fundamental reasons massive stars cannot continue fusion indefinitely. You let your mind rest with the idea that once the core fills with iron, the star loses its last source of outward support. The core now begins to contract rapidly, and as you focus on this inward movement, you understand that gravity pulls the matter into a smaller and smaller region. The pressure increases beyond what electrons can sustain, forcing electrons and protons to combine into neutrons. This process, known as electron capture, releases a burst of neutrinos. These neutrinos escape almost instantly, carrying away energy. The existence of this step is not theoretical. It was confirmed through the detection of neutrinos from supernova 1987A, recorded by multiple observatories on Earth. You reflect on how these faint particles, nearly massless and barely interacting with matter, provided one of the most direct glimpses into the collapse of a stellar core. As the core contracts into nuclear densities, it reaches a point where the inward motion suddenly halts. Neutron degeneracy pressure briefly stops the collapse. The outer layers, still falling inward at high velocities, strike this rigid core. The impact creates a powerful shock wave. Initially, this shock wave stalls, but the enormous flood of neutrinos streaming from the core transfers enough energy to revive it. This understanding comes from decades of simulation work supported by observed supernova light curves and spectra. You let the idea unfold gently. The shock pushes outward, and the entire outer envelope of the star is blown into space. The supernova becomes visible across vast cosmic distances, shining as brightly as an entire galaxy for a short time. Yet in your mind, you hold it softly, not as a violent event but as a natural, evidence-supported phase of stellar evolution. You allow yourself to picture what remains at the center. If the original star was massive enough, the iron core that collapsed now sits as a compact remnant. Whether this remnant becomes a neutron star or continues collapsing into a black hole depends on mass and the physics of dense matter. You recall that neutron stars typically form when the core mass is around 1 to 2 times that of the Sun. Observations of pulsars, gravitational wave mergers, and X-ray measurements support this mass range. If the core is above a certain threshold, no known pressure can resist further collapse, and a black hole forms. In this way, the end of a massive star is not ambiguous but follows a clear, evidence-based pathway determined by well-tested physical laws. You bring your focus to the surroundings of such a star after the explosion. Astronomers have studied the remains of many supernovae, such as the Crab Nebula and Cassiopeia A. These expanding clouds show the redistributed elements the star created during its life. Spectra reveal oxygen, carbon, calcium, iron, and many heavier elements. You understand that these observations confirm the star's internal fusion stages and show how the universe becomes enriched over time. You rest in the factual understanding that the elements making up planets, rocks, oceans, and even your own body come from stars that ended in these precise ways. This knowledge remains grounded in spectroscopy, laboratory measurements of atomic transitions, and studies of cosmic abundances. You let your attention return once more to the collapse itself. The timing, energy release, and neutrino detection make the process one of the most thoroughly studied large-scale transformations in astrophysics. The physics that governs it, from nuclear reactions to gravitational collapse, is consistent across models, experiments, and observations. You remind yourself that although supernovae may appear unpredictable from a distant perspective, their internal workings follow measurable and repeatable rules. This steadiness makes the end of a massive star one of the most scientifically grounded transitions in the universe. With these ideas resting quietly in your mind, you sense how everything begins with the gradual loss of fusion pressure and ends with the formation of something far denser than the original star. You hold the entire sequence gently. The layering of fusion products, the arrival of iron, the collapse of the core, the burst of neutrinos, the outward shock, and the emergence of a compact remnant. Each step fits into a larger scientific picture supported by observation, measurement, and theory. As you let the image fade into calm space, you begin to sense the importance of understanding what happens to the collapsed core itself, the place where gravity meets matter at extraordinary density and gives rise to the compact objects that shape the next part of the story. You begin by letting your thoughts settle on the idea of matter under extreme pressure. You picture a region where atoms no longer behave in familiar ways, not because of imagination but because of what measurements and theory show. A neutron star is one of the places in the universe where matter reaches densities that push against the limits of nuclear physics. You let that idea feel quiet and steady as you explore what such an object truly is. You recall that a neutron star forms when the core of a massive star collapses during a supernova. The collapse forces electrons and protons to combine, producing neutrons. These reactions create a core made almost entirely of neutron-rich matter. You focus gently on the fact that this transformation is not a guess but the outcome of nuclear interactions studied in laboratories and confirmed through astrophysical observations. What remains is a compact sphere with a radius of about 10 to 14 kilometers. You sense how small that is compared to the mass it holds, often between 1 and 2 times the mass of the Sun. You let the contrast settle in your mind. A sun's worth of mass inside a volume smaller than a large city. You consider the density implied by this combination of mass and size. The numbers come from calculations grounded in general relativity and measurements of pulsar masses in binary systems. The density reaches values far beyond atomic nuclei, reaching around 1 billion tons per cubic centimeter. You let the number sit quietly, knowing that it reflects the limits of matter rather than an exaggeration. This density creates a state in which neutrons form the bulk of the material, supported against further collapse by quantum mechanics. As you hold this thought, you begin to sense how different a neutron star is from a normal star, where atoms remain intact and plasma behaves according to everyday electromagnetic interactions. You now let your attention drift to rotation. Neutron stars rotate with speeds that come directly from the conservation of angular momentum. The collapsing core shrinks dramatically during formation, and the rotation rate increases to maintain angular momentum. Observations of pulsars show spins ranging from a few times per second to hundreds of times per second. You consider the fastest known pulsars, spinning more than 700 times per second. These numbers come from precise timing measurements of radio pulses, recorded with microsecond accuracy. You sense how remarkable it is that such stability exists in these signals, allowing astronomers to use pulsars as cosmic clocks. You then focus gently on magnetic fields. Neutron stars possess some of the strongest magnetic fields measured in the universe. Typical neutron stars have magnetic fields trillions of times stronger than Earth's. Magnetars, a specific class, have magnetic fields even stronger, reaching around 10,000 trillion times Earth's magnetic field. These values come from observations of X-ray bursts, spin-down rates, and emission signatures. You let the numbers settle, not as dramatic exaggerations but as reliable results derived from decades of monitoring. The presence of such magnetic fields arises naturally from the compression of the star's original magnetic field during collapse. The physics behind this intensification follows established principles of magnetic flux conservation. You now look inward again, sensing the structure inside the star. Although direct observation of the interior is impossible, scientists infer certain layers through nuclear physics and the behavior of matter at high densities. The outermost region is thought to be a solid crust made of atomic nuclei arranged in a dense lattice. This understanding comes from combining laboratory measurements of nuclear interactions with the behavior of matter under extreme pressure. Beneath the crust lies a region where neutrons begin to drip out of nuclei, forming a superfluid. You let this idea remain factual. A superfluid is a state of matter where friction drops to nearly zero, confirmed through experimental physics. Deeper still, the density increases until nearly all matter becomes a uniform sea of neutrons with small fractions of other particles. Everything here is grounded in calculations supported by laboratory data and astrophysical constraints. You contrast this gently with a black hole and a normal star. A normal star has a large radius, a surface of hot plasma, and energy produced by fusion. A black hole has no surface at all, only a boundary where the escape velocity reaches the speed of light. A neutron star sits in between, possessing a real surface made of dense nuclear matter. You let this difference stand clearly. A neutron star emits thermal radiation, radio pulses, and X-rays. A black hole emits none of these on its own. These distinctions arise from observation, not assumption. A neutron star can be seen directly through its pulses or thermal glow. A black hole must be inferred through its gravitational influence or radiation from nearby gas. You shift your attention to how neutron stars are detected. Many neutron stars are seen as pulsars, their beams sweeping past Earth as they rotate. Others are identified through X-ray emissions when they accrete matter from companion stars. Some appear in gravitational wave data when two neutron stars orbit each other closely and eventually merge. All these methods provide independent confirmation of neutron star properties. You rest in this evidence, feeling the clarity that comes from multiple ways of observing the same kind of object. You gently explore the limits of what a neutron star can be. Its mass cannot be too small or too large. Too small and the object cannot reach nuclear densities. Too large and the star collapses into a black hole. Observation has revealed neutron stars with masses around 2 solar masses, and these measurements help refine models of nuclear matter. You sense how this boundary creates a stable range where neutron stars can exist. Everything inside this range lines up with equations tested through experiments, astrophysical data, and gravitational wave events. With these concepts resting together, you picture a neutron star as a compact sphere with a strong gravitational field. Yet it remains distinct from a black hole because light can leave its surface. You can see pulsar flashes. You can measure thermal radiation from the surface. You can observe how matter interacts with the star's crust and magnetic field. These observations give scientists the ability to determine mass, radius, density, and spin with increasing precision. You hold this in your mind as a reminder that the object is not defined by uncertainty but by the data collected from telescopes and detectors. As your mind settles into these details, you sense how neutron stars feel less mysterious and more like well-understood physical systems. Their rotation arises from angular momentum. Their magnetic fields come from flux conservation. Their density follows directly from the collapse of massive stellar cores. Their observational signatures match what theory predicts. You feel the steadiness in knowing that the extreme properties of neutron stars come from the same physical laws that govern matter in laboratories, simply pushed to higher pressures and densities. You let your attention ease into the broader picture, where a neutron star represents matter balanced at the edge of collapse. It sits at a point where gravity pulls inward with enormous strength, but quantum pressure resists further contraction. You sense that this delicate balance defines the neutron star's identity. The properties you have followed, mass, radius, density, magnetic fields, rotation, are all consequences of this balance. The object remains stable as long as its mass stays within the range allowed by nuclear physics. In this calm space, you feel how understanding these dense remnants prepares your mind to explore the boundary where stability ends and collapse continues. The line between holding firm and falling inward carries its own deep clarity, shaped by the laws of gravity and matter. You begin by picturing the final moments of a massive star's life, not the fiery beauty of the supernova explosion itself, but the quiet, hidden process happening deep within its core. The outer layers have been blasted away. Light, heat, and radiation race outward into space. Yet at the very center, what remains is a tiny remnant left to face gravity alone. You follow that inward pull, recognizing that gravity wants only one thing: to compress, to shrink, to collapse the core as far as the laws of physics will allow. At first, matter resists. Even in the dying moments of a star, familiar atoms still try to hold their shape. But the supernova's inward shock is too strong. Electrons are crushed into protons. The boundaries of ordinary matter dissolve. Now you are left with neutrons, closely packed, unimaginably dense, forming something that is no longer a normal atomic structure. This is where collapse slows, and you begin learning the real reason why it does not continue forever. You encounter neutron degeneracy pressure, a quiet but powerful force rooted in quantum mechanics. Every neutron, like every electron, is a quantum particle with a deep rule governing its behavior. No two identical fermions can occupy the same quantum state. This rule, known as the Pauli exclusion principle, sounds abstract, but here it becomes physical. It becomes structure. It becomes resistance. As gravity squeezes neutrons closer and closer, they push back, not out of heat or motion or charge, but because the fundamental fabric of quantum mechanics will not allow them to be forced into identical states. This pressure halts the star's collapse, at least for a time. You imagine the inward fall slowing, the crushing weight of gravity meeting this quiet, invisible force. A balance forms. Out of that balance, a neutron star emerges. Tiny, immensely dense, and stable. It is not stable because gravity becomes weaker, but because degeneracy pressure grows strong enough to fight back. Yet you quickly learn that this balance is delicate. Gravity never stops trying to pull inward. Degeneracy pressure never stops trying to resist. The neutron star exists only because these two forces find equilibrium. But you also discover that this equilibrium has a limit. It is not infinite. It is not unbreakable. Can be exceeded. To understand this boundary, you follow the work of physicists who asked a simple question. How much mass can neutron degeneracy pressure hold up against gravity? Their answer required careful mathematics, rooted in general relativity and nuclear physics. Eventually, this reasoning became the Tolman-Oppenheimer-Volkoff limit, often shortened to the TOV limit. Instead of treating gravity Newtonianly, it uses the full curvature of spacetime predicted by Einstein's equations. Instead of treating neutrons as ideal particles, it includes their real physical interactions. You now learn what this limit means. It is the maximum mass that a neutron star can have before even degeneracy pressure can no longer counter gravity. Physicists estimate this threshold to be roughly 2 to 3 solar masses, based on observed neutron stars, nuclear equations of state, and gravitational wave data. Below this limit, a neutron star can withstand its own gravity. Above it, collapse becomes unstoppable. You picture a neutron star slowly gaining mass, perhaps by pulling gas from a companion star, or merging with another neutron star, or forming from a core that is simply too heavy from the start. First, nothing happens. The star remains stable. But as the mass creeps closer to the TOV limit, its radius shrinks. Gravity increases. The internal pressure necessary to resist collapse rises. Neutrons are packed tighter than before, and nuclear forces strain at their boundaries. The star becomes denser, hotter in its interior, more curved in its spacetime. Once the TOV limit is crossed, the final stage begins. Neutrons can no longer maintain the exclusion rule effectively. Even the strong nuclear force, the most powerful force known in the universe, cannot provide the additional support required. Collapse resumes. But this time, it does not slow or find another stopping point. No new form of matter or pressure emerges in time. Nothing holds back the fall. You witness the heart of the star shrinking rapidly. It becomes smaller than any nuclear scale you have ever imagined. Gravity's pull steepens. Space around it curves so sharply that even light struggles to escape. Soon, an event horizon forms. The boundary beyond which nothing can return. A black hole has been created. You realize this transformation is not violent in a fiery sense. It is silent, inevitable, and governed by the clean lines of physical law. This is the moment when you truly grasp the meaning of gravitational collapse. It is not chaos or mystery. It is the calm working out of mass, pressure, and quantum mechanics. A neutron star exists because matter can resist gravity. A black hole forms because gravity eventually becomes stronger than any known form of pressure. You reflect on how this boundary helps distinguish neutron stars from black holes in the real universe. Neutron stars are observed with masses around 1.2 to 2.2 solar masses. Black holes, by contrast, almost never appear below roughly 3 solar masses. Observations from LIGO, Virgo, NICER, and radio telescopes all support this separation. The TOV limit is not merely a theoretical idea. It is reflected in the distribution of objects across the cosmos. The science becomes clearer when you visualize the internal processes. A neutron star is a structure. A solid crust, a superfluid interior, and densely packed neutrons that maintain pressure. A black hole, by contrast, has no surface and no interior in the way matter normally defines it. There is no physical object resisting collapse. There is simply spacetime curved around a center so dense that all trajectories lead inward. You begin to appreciate why a neutron star cannot simply continue collapsing in small steps. The moment its mass crosses the threshold, equilibrium is lost. Gravity does not gradually overpower neutron pressure. It overwhelms it fully and immediately once the limit is exceeded. In that sense, the TOV limit is not merely a number. It is a structural boundary, a tipping point, a point of no return for stellar matter. By the end of this chapter, you recognize that the universe is orderly in its extremes. Collapse stops at a neutron star because quantum mechanics forces it to. Collapse continues into a black hole because mass and gravity exceed that quantum boundary. There is no guesswork in separating the two, only physics, evidence, and the deep rules governing matter at its most compressed. You begin this chapter by imagining yourself standing in a quiet control room. The lights low, the screens glowing with traces of signals taken from across the cosmos. You are not looking directly at neutron stars with your eyes, because no ordinary telescope can show their surfaces in detail. Instead, you learn that astronomers use patterns, pulses, and spectra to understand what these extraordinary objects truly are. You realize quickly that observing neutron stars is less like taking a picture and more like listening to a finely tuned orchestra of signals. Your first step is into the world of radio pulsar timing, a method that has transformed tiny rotating stars into some of the most precise natural clocks in the universe. A neutron star with a strong magnetic field and rapid rotation emits beams of radiation from its magnetic poles. As the star spins, these beams sweep across the sky like lighthouse beams. When Earth lies in their path, the signal arrives as regular pulses of radio waves. You picture these pulses appearing on a screen as sharp, repeating spikes, clean, steady, and astonishingly precise. You learn that some pulsars rotate hundreds of times per second, their signals arriving with timing stability that rivals atomic clocks. When astronomers measure these pulses, they can determine the star's rotation rate to many decimal places. If a neutron star speeds up, slows down, or shifts position slightly, the timing changes. These variations reveal the star's mass, its motion through space, and even the presence of companion stars. By watching the arrival time of each pulse, astronomers create a detailed map of the star's behavior. From pulsar timing, you move gently into the realm of X-ray astronomy. While radio emissions tell you about rotation, X-ray spectra tell you about temperature, magnetic fields, and the conditions at the star's surface. When matter falls onto a neutron star from a surrounding disk or a companion star, it heats to millions of degrees. At those temperatures, matter radiates X-rays. Even isolated neutron stars emit faint X-rays from their hot surfaces. You imagine viewing these X-rays through detectors on satellites high above Earth's atmosphere, each photon carrying information about the star's energy and environment. You then learn how X-ray spectra can reveal the star's radius. If astronomers know the surface temperature and the amount of radiation reaching Earth, they can infer how large the neutron star must be to produce that signal. Because neutron stars have such tiny radii, even small measurement differences matter. Their surfaces behave differently than any normal star, and X-ray data allow scientists to detect that difference. From here, you step into the world of NICER, an instrument mounted on the International Space Station. NICER was built specifically to measure the size and structure of neutron stars with unprecedented precision. It watches tiny fluctuations in X-ray brightness as the star rotates, mapping how the beam changes due to the star's shape, gravity, and hot spots. You envision NICER's detectors catching each photon, timing it, and piecing together a physical model of the star's surface. Through this technique, astronomers can determine the star's radius to within a few hundred meters, a remarkable achievement for an object over 1,000 light-years away. NICER's work connects directly to the equation of state of neutron star matter, the relationship between pressure and density inside the star. By carefully measuring mass and radius together, astronomers constrain which theoretical models match reality. In this way, NICER provides not just images of neutron stars, but insights into the physics governing their interiors. You now shift to a different kind of observation, one that does not rely on light at all: gravitational wave detection. With instruments like LIGO and Virgo, astronomers listen for ripples in spacetime produced when two neutron stars spiral together and merge. The gravitational waves produced in these final minutes carry information about mass, radius, tidal deformability, and internal structure. You imagine the signal rising in pitch, a cosmic chirp that ends abruptly when the stars collide. From this chirp, scientists extract parameters that were once completely inaccessible. For example, the way each star distorts under the other's gravity depends on its stiffness and density, exactly the properties governed by nuclear physics. These distortions leave imprints in the gravitational wave signal. When LIGO detected the first neutron-star merger, astronomers realized they had gained a direct, independent method of confirming neutron stars' physical properties. The measurements of mass and radius from gravitational waves matched what had already been learned from radio and X-ray methods. Having explored radio, X-ray, and gravitational wave techniques, you now observe how these approaches work together. Radio pulsar timing provides precise rotation rates and mass measurements, especially for neutron stars in binary systems. X-ray spectra and NICER's modeling give insight into radius, temperature, and surface conditions. Gravitational wave detections offer information about deformability and internal structure. When these methods align, they reinforce each other. When small differences appear, they guide scientists toward more accurate models. This combination of methods also helps distinguish neutron stars from black holes. A neutron star's pulsations cannot come from a black hole, which has no surface and no rotating magnetic beam. The X-ray emission from a neutron star's surface shows a thermal spectrum that a black hole cannot produce. And gravitational wave signals from neutron star mergers differ from black hole signals. Neutron stars deform before merging, while black holes do not. These differences appear clearly in the data. By learning how each observation works, you understand how scientists separate these two types of objects with confidence. You return now to the control room in your imagination, but this time you see more clearly how the instruments work together. You picture a radio telescope array stretching across thousands of kilometers, collecting pulses from a distant pulsar. You imagine orbiting X-ray telescopes like Chandra and XMM Newton observing the hot surfaces and magnetic fields of neutron stars. You recall NICER's dedicated work mapping radii with exquisite sensitivity. And you hear the faint, rising tone of gravitational waves detected by interferometers on Earth. Each method gives a piece of the puzzle. Together, they build a physical portrait that is far more detailed than any single technique could provide. You now explore how astronomers measure mass with extraordinary precision. In binary pulsar systems, radio timing reveals how the pulsar's motion is affected by the gravitational pull of its companion. Certain timing effects, such as the Shapiro delay, where pulses take slightly longer to reach Earth when passing near the companion's gravity, allow astronomers to calculate the star's mass directly. This method has been used to measure neutron stars heavier than 2 solar masses, confirming the upper range of stable neutron star masses. To measure radius, X-ray data from NICER and other observatories are essential. When hot spots on a neutron star rotate in and out of view, the brightness changes slightly. The strength and timing of these changes depend on the star's size, shape, and gravitational bending of light. By modeling these variations, astronomers extract radius values around 11 to 14 kilometers for typical neutron stars. To measure spin, both radio and X-ray observations contribute. Millisecond pulsars, neutron stars spun up to rapid rotation by accreting matter, can rotate more than 700 times per second. The extraordinary stability of these pulses allows astronomers to track changes caused by glitches, magnetic field decay, or interactions with nearby stars. Finally, you see how gravitational wave detectors contribute to internal structure measurements. During neutron star mergers, tidal effects imprint themselves on the gravitational wave signal. These effects depend on the star's stiffness, which is dictated by nuclear physics. By analyzing these distortions, astronomers estimate how compressible neutron star matter is, providing evidence that supports and refines the measurements from X-ray and radio observations. You now step back and reflect on the full picture. Observing neutron stars up close is not a single technique or a single type of signal. It is a symphony of methods, each bringing unique strengths. Radio pulses give timing and mass. X-rays give temperature, magnetic fields, and radius. Gravitational waves give deformability and internal structure. Together, they confirm that neutron stars are real, distinct, and physically well understood objects. Not speculative, not hidden, and not easily confused with black holes. By the end of this chapter, neutron stars feel closer. Their radiation patterns, their thermal glow, and even their gravitational echoes reach across cosmic distances. You realize that humanity's instruments can observe them with remarkable clarity, and that the evidence they provide is consistent from every angle. Through these methods, neutron stars stand revealed as concrete, measurable, and profoundly physical. You begin by letting your mind settle into a quiet understanding of what a black hole truly is. The idea may feel dramatic at first, but as you breathe slowly, you recognize that a black hole is simply a consequence of gravity taken to its natural limit. Nothing about this object is magical or mysterious. It follows the same physical laws that guide planets, stars, and your own world. What makes a black hole special is that gravity becomes so strong that nothing, not even light, can move fast enough to escape. As this understanding settles in, the concept feels calm, precise, and firmly grounded in general relativity. You picture a mass compressed into a region so small that the escape velocity exceeds the speed of light. This is the defining threshold. When mass is squeezed past a critical radius, gravity dominates completely. That radius is described by the Schwarzschild radius, a distance determined only by the object's mass. You do not need to imagine anything exotic inside it. All you need is the recognition that once matter passes this boundary, light can no longer climb out. The surface defined by this radius is not a physical surface like a star's crust. It is a mathematical boundary called the event horizon. Nothing remarkable happens at the horizon itself. If you could fall toward a black hole, an idea you consider only as a mental exercise, you would feel nothing special when crossing this radius. Yet, to a distant observer, everything changes. Light emitted just outside the event horizon becomes stretched and slowed by gravity, a process known as gravitational redshift. Signals weaken, dim, and fade as the object approaches the threshold. From far away, the collapse appears to slow endlessly, even though from the object's own point of view, the journey continues smoothly. These effects come directly from Einstein's equations. They are measured, predictable, and repeatable. You then focus on the mass itself. A black hole can be formed from stars that collapse beyond their ability to resist gravity. When this happens, no known form of pressure can hold the matter up. The collapse continues until all the mass fits inside the event horizon. Nothing can counterbalance gravity at this stage. The star's internal structure disappears from view. From the outside, only three measurable quantities remain: mass, spin, and charge. This is known as the no-hair principle, a statement supported by both theory and observation. A black hole does not keep a surface or a crust. It has no solid boundary from which radiation can reflect or emerge. You now consider how black holes are detected, since by definition they emit no light from within the event horizon. The first method comes from the behavior of matter around them. As gas spirals inward, it forms an accretion disk. Friction and compression heat the gas to extremely high temperatures, producing X-rays. These X-rays vary in brightness and spectrum based on the black hole's mass and spin. When astronomers observe this light, they are seeing the conditions just outside the event horizon, not inside it. Yet these observations provide strong evidence for the presence of a compact object too small and too massive to be anything else. You imagine a binary system in which a black hole pulls matter from a companion star. This material glows brightly as it accelerates and heats, and the brightness changes over time. From these changes, astronomers calculate mass. If the compact object is heavier than the maximum known mass of a neutron star, and it lacks pulsations or surface emissions, it must be a black hole. The measurements are consistent and repeatable. They come from well-tested physics. You then explore how gravitational waves provide another method for identifying black holes. When two black holes spiral toward each other, their motion produces ripples in spacetime. Instruments like LIGO and Virgo detect these ripples as faint stretches and squeezes in length, measured with astonishing precision. The signals tell astronomers the masses of the merging black holes and how their orbits changed over time. Black holes produce a very specific pattern. They merge without any sign of tidal deformation, and the final moments show a ring-down signal that matches the predictions of general relativity. When such a signal is observed, the conclusion is supported by every aspect of the data. Only black holes create that pattern. Another method involves studying the motion of stars orbiting unseen masses. You imagine a dense region such as the center of our galaxy. Stars there move in tight, fast orbits. By measuring their positions, velocities, and accelerations, astronomers determine the mass causing the motion. At the Milky Way's core, this method revealed an object of about 4 million solar masses confined to a region smaller than our solar system. No cluster of normal stars could remain stable in such a tiny volume. No neutron star could achieve such mass. The only explanation supported by physics is a supermassive black hole. You picture the Event Horizon Telescope, an array of radio telescopes linked across Earth. By combining signals from many locations, it produces extremely high-resolution images. When this array observed the region around the black hole in the galaxy M87, it detected a bright ring of emission surrounding a central dark area. The ring's size matched the predicted shadow of a black hole's event horizon. This was not a direct picture of the interior, but an image of the glowing disk and the light bent by the black hole's gravity. The shape and scale of this ring were precisely what the equations predicted. You then focus gently on the differences between black holes and other compact objects. While neutron stars have surfaces, black holes do not. While neutron stars emit pulses through magnetic beams, black holes cannot produce such pulses. While neutron stars can resist collapse up to a certain mass, black holes have no such limit once the collapse begins. These differences arise from fundamental aspects of gravity, pressure, and nuclear forces. They do not overlap. They create clear categories that astronomers use to classify celestial objects with confidence. As you let these ideas settle, you explore what happens to light near a black hole. Light passing close to the event horizon bends sharply, curving around the object or becoming trapped in unstable orbits. This gravitational lensing is not a distortion of the light's nature. It simply follows the curvature of spacetime. When you imagine looking at a black hole surrounded by stars, you would see rings and arcs formed by bent light paths. These features have been observed around massive objects and match the predictions of relativity. You then consider how time behaves near a black hole. Clocks in strong gravitational fields run more slowly compared to those far away. This is called gravitational time dilation. For a clock near the event horizon, time passes at a slower rate. These effects are not hypothetical. They have been measured in weaker gravitational fields near Earth and verified repeatedly. The same equations extend naturally to stronger fields near black holes. The behavior is smooth, continuous, and grounded in precise mathematics. You reflect on the simplicity of a black hole's requirements. If enough mass is compressed inside the Schwarzschild radius, a black hole forms. There is no alternate mechanism that prevents this collapse once the threshold is passed. There is no pressure strong enough to counteract gravity at this scale. This understanding is why the distinction between neutron stars and black holes is so sharp. Neutron stars have an internal structure held up by nuclear forces. Black holes represent the point at which those forces are no longer sufficient. You now imagine the calm clarity that comes from knowing exactly what defines a black hole. It is not hidden or disguised. It does not imitate other objects. It is simply matter compressed so deeply that gravity shapes spacetime into a region from which light cannot escape. Everything observable around it follows directly from this definition. The accretion disks, X-ray emissions, gravitational waves, orbital motions, and lensing patterns all come from well-understood physical processes. As you breathe gently, you allow the final thought to settle. The universe provides ways to distinguish objects even when they are distant and compact. With careful observation, the nature of a black hole becomes unmistakable, and the physical clarity of gravity's strongest expression becomes a guide toward deeper understanding of matter, energy, and the structure of spacetime itself. You begin by centering your mind on the clear, measurable features that distinguish neutron stars from black holes. Both objects arise from collapsed stars, yet each obeys the laws of physics in ways that reveal their differences unmistakably. You focus on mass first. Neutron stars generally have masses between about 1.2 and 2.2 times that of the Sun. Observations of pulsars in binary systems and neutron star mergers provide these numbers with remarkable precision. Black holes, in contrast, almost never appear below 3 solar masses, a boundary that reflects the point at which gravity overwhelms any internal pressure. Mass alone offers a strong, observable distinction between these two objects. Next, you consider radius. A neutron star's radius typically spans only 10 to 14 kilometers. The size is inferred through thermal X-ray measurements, pulse profile modeling, and gravitational wave data. A black hole has no physical surface. Its defining radius, the Schwarzschild radius, is a boundary for the escape of light, not a material surface. For a black hole of 2 to 10 solar masses, this radius may be several kilometers, but unlike a neutron star, nothing emits radiation from within it. The existence of a solid, measurable surface immediately separates neutron stars from black holes. You let your attention drift to density. Neutron stars are incredibly dense, with values reaching around 1 billion tons per cubic centimeter. The core consists of neutrons packed so tightly that atomic structure is essentially lost, and the material is held up against gravity by neutron degeneracy pressure. Black holes, by contrast, do not have a measurable internal density in the conventional sense. Their mass is concentrated within the event horizon, which defines a region from which nothing escapes. Observers infer their properties from interactions with surrounding matter, not by measuring a surface. The contrast between the high but definable density of neutron stars and the theoretical singularity of black holes is absolute. You now follow rotation rates. Neutron stars often rotate hundreds of times per second, and the most extreme millisecond pulsars reach more than 700 revolutions per second. This rotation is measured through the timing of radio pulses or periodic X-ray emission. Black holes also spin, and their angular momentum can be inferred from accretion disk behavior and gravitational wave signals. However, they do not produce the regular pulsations characteristic of neutron stars. The presence or absence of observable pulses is a clear, measurable marker. Your mind absorbs the difference. Neutron stars have a structured, rotating surface emitting periodic signals. Black holes have no surface and therefore no direct periodic emission. You move to magnetic fields, which offer another striking distinction. Neutron stars often possess magnetic fields trillions of times stronger than Earth's. Magnetars, a subclass, can have fields up to 10 to the power of 15 Gauss. These fields are measured using X-ray spectroscopy, spin-down rates, and observation of high-energy bursts. Black holes have no inherent magnetic field. Any observed field in a black hole system comes from the accretion disk or the surrounding plasma. The contrast is so dramatic that the presence of a strong, structured magnetic field is an unmistakable indicator of a neutron star rather than a black hole. You reflect gently on observable emissions. Neutron stars radiate in radio, optical, X-ray, and sometimes gamma-ray bands. The pulses arise from the rotation of the magnetic poles. The thermal radiation comes from the hot surface, while bursts from magnetars are linked to magnetic reconnection in the crust. Black holes emit no radiation from inside the event horizon. Any X-rays or gamma rays originate from infalling matter, not the object itself. Observing a periodic signal, a thermal surface glow, or a sudden magnetic burst confirms a neutron star. The lack of such signals in other massive, compact objects points to a black hole. These distinctions are measurable, repeated, and grounded in decades of data. You now consider orbital behavior in binaries. Neutron stars in binary systems display mass transfer effects, pulsar timing shifts, and orbital decay that can be precisely modeled. Black holes in binaries show accretion disk X-ray emission, but no pulsar pulses or surface radiation. Gravitational interactions allow astronomers to calculate the masses involved, providing further evidence that each object is distinct. The difference between an observable surface and a purely gravitational object ensures that the two types of remnants are distinguishable in practice. You gently examine gravitational wave signatures. When neutron stars merge, their tidal deformation leaves detectable imprints in the waveforms. The final mass and radius affect the pattern of the chirp. When black holes merge, the waveform is simpler. No tidal deformation occurs, and the ring-down signal corresponds to the properties of spacetime surrounding the merged event horizon. By comparing waveforms from different mergers, scientists can confirm whether the objects involved were neutron stars, black holes, or a combination. Gravitational waves provide independent, high-precision evidence for distinguishing the two classes. You pause to consider how theoretical predictions align with observations. Every property you have examined, mass, radius, density, rotation, magnetic field, emissions, binary dynamics, gravitational waves, is predicted by well-established physics. Nuclear physics, quantum mechanics, and general relativity provide equations that describe each phenomenon. Observational data from pulsars, X-ray telescopes, and gravitational wave detectors consistently match these predictions. The results are mutually reinforcing, creating a scientific picture in which neutron stars and black holes occupy separate, well-defined regimes. You also note how the TOV limit underlies these differences. No neutron star has been observed above approximately 2 solar masses. Beyond this point, neutron degeneracy pressure is insufficient, and collapse into a black hole occurs. Black holes have masses that exceed this limit, often significantly. Observational data confirm this. The lightest black holes observed in X-ray binaries are heavier than the most massive neutron stars, reinforcing the physical distinction. You see how these limits are not arbitrary, but consequences of the known laws of physics. You return to the magnetic and thermal signatures one last time. No black hole has a surface to host a magnetic field anchored in solid matter. Neutron stars, with their crusts and strong magnetic fields, emit bursts, pulses, and thermal radiation. Each observed pulsar pulse, each X-ray spectrum, each magnetar flare provides direct evidence of surface activity. These measurements confirm what theory predicts. Neutron stars cannot be black holes in disguise, and black holes cannot produce surface phenomena. As your mind absorbs all these details, you feel the clarity of the distinctions. Neutron stars have solid surfaces, strong magnetic fields, measurable radii, periodic pulses, and precise masses below the TOV limit. Black holes have no surface, no inherent magnetic field, no direct radiation, and masses above the collapse threshold. Observational evidence across multiple wavelengths and gravitational wave channels consistently supports this division. The scientific picture is not fuzzy or speculative. It is concrete, repeatable, and entirely evidence-based. You now rest in the calm understanding that nature itself separates these objects. The universe provides mass limits, surface activity, magnetic behavior, and gravitational signatures that clearly define each type. By following these signals, you recognize that neutron stars and black holes are distinct not by imagination, but by measurement. There is no ambiguity when the full range of evidence is considered. You feel a steady reassurance in knowing that extreme physics, while intense, is predictable and understandable. Finally, you allow your attention to drift toward the broader context. These differences do not exist in isolation. Each measured property ties into the fundamental physics of gravity, quantum mechanics, and nuclear interactions. The neutron star's resistance to collapse, the black hole's absolute dominance of spacetime, the radiation patterns and rotation rates, all emerge from well-tested laws. As you let these ideas settle, you sense that the universe's rules are consistent even in its most extreme objects. Observing, measuring, and comparing these remnants brings clarity, precision, and calm certainty. With this understanding resting gently in your mind, you feel prepared to explore the next layer of extreme physics. How matter behaves at the densities found inside neutron stars, and how the equation of state governs whether these dense remnants remain stable or succumb to collapse. You begin by focusing on the heart of a neutron star, the region where matter exists in conditions unlike anything on Earth. You feel the quiet power of the forces at play, and you understand that these extremes are not imagined, but measurable through observations and theory. The central concept guiding your attention is the equation of state, a relationship between pressure, density, and temperature that describes how matter responds to compression. This equation is not abstract. It governs whether a neutron star remains stable or collapses into a black hole. It is a precise, physical boundary written into the laws of the universe. You explore how the equation of state arises from nuclear interactions. Neutrons, being fermions, resist being squeezed into identical quantum states due to the Pauli exclusion principle. At the same time, the strong nuclear force operates at very short ranges, providing both repulsion and attraction depending on separation. The balance between these interactions determines how much pressure builds for a given density. Unlike ordinary matter, which can be compressed with relatively modest forces, neutron star matter is almost incompressible. You sense that this rigidity is what allows a neutron star to exist against the pull of its enormous gravity. Next, you consider observational constraints on the equation of state. X-ray measurements, such as those from NICER, provide estimates of a neutron star's radius and mass. When these measurements are compared to theoretical models, only certain equations of state are compatible. Too soft a model would produce stars smaller than observed. Too stiff a model would allow masses higher than those detected. Gravitational wave signals from neutron star mergers add further constraints, showing how the stars deform under tidal forces. Each observation narrows the possibilities, producing a realistic, testable understanding of matter under extreme density. You reflect on how mass and radius measurements combine to constrain the interior. The larger the mass for a given radius, the stiffer the equation of state must be to resist collapse. Conversely, small radii for typical masses imply softer matter. NICER and other X-ray missions track variations in pulse profiles to determine both quantities with unprecedented precision. These measurements provide direct evidence that neutron stars have solid structures and measurable surfaces, and that they differ from black holes, which have no such surfaces or radii. Your mind settles on the clarity this brings. The physics is precise, repeatable, and grounded in observation. You explore the role of gravitational waves more closely. During neutron star mergers, the star's shapes distort due to tidal interactions. The resulting gravitational wave signal encodes information about how easily each star deforms, which depends directly on the equation of state. A stiffer interior resists deformation, producing a distinctive signature. A softer interior deforms more, producing a different pattern. By comparing the signals from multiple mergers, scientists refine their understanding of ultradense matter, confirming that neutron stars obey well-defined physical rules, and that their behavior is distinct from black holes. You notice how the Tolman-Oppenheimer-Volkoff limit is also tied to the equation of state. The maximum mass a neutron star can sustain before collapsing depends on how matter behaves at the highest densities. The equation of state dictates the internal pressure for any given density. If the pressure is insufficient, the star cannot resist gravity, and collapse to a black hole is inevitable. Conversely, the correct balance produces a stable neutron star. You realize that the limit is not arbitrary. It emerges directly from the combination of quantum mechanics, nuclear forces, and relativity. The line between neutron stars and black holes is defined by matter itself. You turn your attention to the crust and outer layers. The outer crust is composed of nuclei embedded in a sea of electrons. Deeper, the inner crust contains neutron-rich nuclei and superfluid neutrons. The equation of state governs how these layers respond to compression and strain. Observations of pulsar glitches, sudden changes in rotation rate, provide indirect evidence of superfluidity and the rigidity of the crust. These events, although small in scale, confirm theoretical predictions about the behavior of dense matter. Every observation supports the physical models, providing a coherent, testable picture. You explore the core of the neutron star, where densities exceed that of atomic nuclei. Here, exotic states of matter may exist, but only within the bounds allowed by nuclear physics and observational constraints. The equation of state must remain consistent with observed mass-radius relations, rotational stability, and merger dynamics. Even without knowing the exact composition, you can predict the pressure, density, and stiffness of the matter. These predictions align with thermal emission, pulsar timing, and gravitational wave data. Your understanding is rooted in real evidence rather than speculation, creating a calm, orderly view of the star's interior. You consider magnetic fields and rotation, which also relate to the equation of state. Rapid rotation affects the star's shape, slightly flattening it at the poles. Strong magnetic fields exert additional pressure, influencing stability and possibly producing observable bursts. NICER and X-ray telescopes measure surface emission and rotational modulation, providing indirect confirmation of internal structure and stiffness. Every observed property, pulsation frequency, spin-down rate, X-ray emission, feeds back into understanding how matter behaves at extreme densities, reinforcing the link between observation and theory. You now reflect on the precision and consistency of this knowledge. The equation of state is not a speculative guess. It is the product of decades of laboratory nuclear physics, observations of neutron stars, and mathematical modeling grounded in relativity. Every measurement, mass, radius, tidal deformability, pulse profile, refines the model. Observed neutron stars fall neatly within predicted ranges, while black holes occupy a different mass-radius regime. The distinction is measurable, repeatable, and exact, providing a calm, reliable understanding of these extreme objects. Finally, you recognize the elegance of the process. By observing pulsars, measuring X-ray spectra, and detecting gravitational waves, humanity has turned the invisible interiors of neutron stars into quantifiable, testable science. The equation of state governs the physics, and the universe provides data to verify it. You feel a quiet sense of reassurance. Matter behaves predictably, even under the most extreme conditions, and every observation strengthens the scientific framework. As your mind rests on this clarity, you notice how the star's fate, stability or collapse, is determined entirely by the properties of matter itself, guiding the transition between neutron stars and black holes with precise, observable rules. You begin by imagining a neutron star at the very edge of stability. Its mass approaches the Tolman-Oppenheimer-Volkoff limit, the maximum that neutron degeneracy pressure can support. Every particle inside contributes to the balance between gravity and nuclear pressure, and the equilibrium is delicate. You breathe slowly, letting your mind follow the physics rather than the drama. This is not a story of imagination, but a measured journey through the forces that govern matter at its densest. You observe how mass accumulation can push a neutron star beyond this limit. One pathway is accretion from a companion star. Matter slowly falls onto the neutron star, increasing its mass over millions of years. Astronomers measure the incoming material through X-ray observations of the accretion disk, tracking brightness, spectra, and variability. As mass builds, the gravitational pull strengthens. At first, the star adjusts slightly, compressing its core. But eventually, the additional mass surpasses what the nuclear forces can sustain. The collapse is inevitable, and the star crosses a physical threshold into a black hole. Another pathway involves neutron-star mergers, which are observed both in electromagnetic and gravitational wave signals. Two neutron stars orbit each other, emitting gravitational waves that gradually reduce their orbital energy. The stars spiral closer over millions of years. When they collide, the combined mass often exceeds the TOV limit. Gravitational wave detectors record the in-spiral, peak, and post-merger ringdown, allowing scientists to calculate the total mass and the nature of the final object. If the mass is beyond the stability limit, the merged remnant collapses into a black hole almost immediately. You notice how extreme mass from stellar evolution can also produce black holes. Massive stars leave behind cores too heavy to remain as neutron stars. During supernovae, the core compresses, and if the mass exceeds the threshold set by nuclear physics, the collapse continues uninterrupted. No pressure, neutron degeneracy or otherwise, can halt this process. Observations of supernova remnants, combined with stellar evolution models, confirm that stars above a certain initial mass consistently produce black holes rather than neutron stars. Each pathway follows predictable, measurable physics. You now examine why the collapse cannot reverse. Once the TOV limit is exceeded, gravity overwhelms all internal pressures. Unlike earlier stages where neutron degeneracy provides resistance, beyond this threshold the forces cannot stop contraction. The matter compacts further, approaching a region from which light cannot escape. General relativity predicts the formation of an event horizon, and the equations show that no known physical process can provide an outward force sufficient to counteract gravity at this scale. There is no known mechanism to regain stability once this point is passed. You consider observational confirmations. The gravitational wave event GW 170817 involved a binary neutron-star merger. Analysis of the signal indicated the masses involved, and post-merger electromagnetic observations suggested the remnant was either a massive neutron star or collapsed into a black hole. Combined modeling, constrained by the equation of state and the observed masses, showed that collapse to a black hole was highly probable. This example illustrates that the transition from neutron star to black hole is not hypothetical. It is observed, predictable, and governed by physics, not conjecture. You focus gently on the timescales of collapse. For a massive neutron star pushed over its stability limit, the collapse into a black hole is rapid, occurring in milliseconds to seconds. This is incredibly fast compared to stellar evolution timescales, yet entirely consistent with the known physics of gravitational collapse. During this brief interval, the star's radius decreases continuously, density increases, and space-time curvature intensifies. There is no pause or reversal. Observationally, the change is inferred from abrupt alterations in emission patterns, disappearance of pulsations, and gravitational wave signatures. You notice the role of rotation. Rapidly spinning neutron stars can temporarily support slightly more mass than the static TOV limit allows, because centrifugal forces oppose gravity. Millisecond pulsars, for example, achieve rotation rates of hundreds of revolutions per second. However, as they lose energy through magnetic braking or gravitational wave emission, rotation slows. Once centrifugal support decreases, the mass limit returns to its non-rotating value, and if the star exceeds it, collapse proceeds. Rotation influences timing and threshold, but it cannot prevent the fundamental physical transition dictated by pressure and gravity. You explore the connection with the equation of state. The precise density and pressure profiles of neutron star matter determine how much mass can be supported. Different theoretical models predict slightly different maximum masses. Observations of massive neutron stars, combined with gravitational wave data from mergers, narrow these models. When the TOV limit is reached, the star has exhausted all internal pressure mechanisms capable of halting gravity. The collapse is not arbitrary. It follows directly from the interplay between matter and the curvature of spacetime. You now examine gravitational wave evidence of collapse. In mergers, post-merger signals provide clues about whether a stable neutron star remained or a black hole formed. A rapidly fading signal indicates prompt collapse into a black hole, while a longer-lived signal suggests a transient hypermassive neutron star. By studying these waveforms, scientists confirm that the physics of collapse aligns precisely with predictions. The observations match theoretical models, demonstrating that exceeding the mass limit leads predictably to black holes. You consider the disappearance of surface phenomena. A neutron star emits pulsar beams, thermal radiation, and sometimes bursts from magnetars. Once collapse occurs, these signals vanish. There is no surface remaining to emit light or pulses. Observers tracking such an object see the cessation of periodic emission, and any X-ray or gamma-ray signal thereafter comes from the surrounding accretion disk rather than the compact object itself. This provides an additional observational marker, confirming the transition from neutron star to black hole. You reflect on the continuity of physical laws. The collapse process does not break known physics. It obeys the principles of general relativity, quantum mechanics, and nuclear physics. No exotic processes are required, and the transformation follows the predictable consequences of exceeding the maximum supportable mass. You realize that the line between neutron stars and black holes is defined entirely by matter's properties and gravity, not by speculation or interpretation. Finally, you rest in the calm understanding that neutron stars, while incredibly dense and extreme, have a precise limit. When that limit is exceeded, either through accretion, mergers, or the natural mass of a progenitor star, collapse into a black hole is inevitable. Observations across electromagnetic and gravitational wave channels confirm these pathways. The transition is governed by measurable physics, not imagination. Gravity, pressure, rotation, and nuclear forces interact in a way that leaves no ambiguity. You feel the quiet certainty of this process. Neutron stars are distinct, yet capable of becoming black holes when nature's limits are surpassed. You begin by letting your mind rest on the gentle flow of information traveling through space. Light, timing signals, and gravitational waves carry the universe's messages across immense distances. These signals are not abstract. They follow precise physical laws, allowing you to reconstruct the properties of objects that are otherwise invisible. You consider how neutron stars and black holes differ in the ways they interact with and emit this information, and you approach each observation calmly, step by step. You start with neutron stars, where light emerges from a physical surface. Thermal radiation comes from the hot crust, usually in X-rays, though some objects also emit in radio, optical, or gamma-ray bands. Rapidly rotating neutron stars with strong magnetic fields produce pulsar beams, highly collimated emissions from their magnetic poles. As the star spins, these beams sweep across space. To a distant observer, the pulses arrive at regular intervals, which can be measured with extraordinary precision. Observing the timing allows astronomers to determine rotation rates, magnetic field strength, and even changes caused by orbiting companions. You consider black holes where light behaves differently. No light escapes from within the event horizon, so the object itself is dark. All the radiation detected comes from surrounding matter, often an accretion disk of infalling gas. Friction and compression heat this gas to high temperatures, producing X-rays and other energetic emissions. The patterns of these emissions carry information about the black hole's mass, spin, and the structure of spacetime near the event horizon. Unlike neutron stars, there is no pulsing surface emission. All signals come from external interactions. You explore how gravitational lensing reveals differences in the two objects. Neutron stars bend light slightly, consistent with their mass and radius. Black holes bend light dramatically, producing arcs, rings, and shadows. The Event Horizon Telescope, for example, imaged the bright ring surrounding M87's central black hole. This ring is not a surface. It is the light from hot gas orbiting near the event horizon, curved by gravity. Observing these patterns allows scientists to map the extreme warping of spacetime and distinguish black holes from other compact objects. You follow how timing signals provide clarity. Pulsars emit at remarkably regular intervals, making them precise cosmic clocks. Observations of these pulses allow detection of orbiting companions, measurement of orbital decay due to gravitational waves, and even tests of general relativity in strong fields. Black holes do not emit such regular signals, so the presence of periodic pulsation is a reliable indicator of a neutron star. When a pulsar disappears or a signal weakens dramatically, it may indicate mass transfer or other changes, but never a black hole pulse from within the event horizon. You gently examine gravitational waves as a form of information distinct from light. Neutron star mergers produce waves that encode tidal deformation and rotation, while black hole mergers produce simpler waveforms determined solely by mass and spin. LIGO and Virgo detect these ripples in spacetime, and careful analysis allows scientists to reconstruct the masses, orbits, and outcomes of the collisions. By comparing waveforms with theoretical models, the nature of each object becomes apparent, reinforcing the observational distinction between neutron stars and black holes. You consider how spacetime curvature affects the propagation of signals. Near both neutron stars and black holes, gravity bends the paths of photons. Time is dilated in strong gravitational fields, meaning clocks near compact objects tick more slowly relative to distant observers. These effects are measurable. Pulsar timing, Shapiro delays, and gravitational wave propagation confirm the predictions of general relativity. The contrast is particularly pronounced near black holes, where the event horizon marks a region from which no signal can escape, while neutron stars remain observable through their surface emissions. You explore the information carried by orbital dynamics. In binary systems, neutron stars show shifts in pulse timing as they orbit companions. Mass transfer affects brightness and rotational spin, all of which can be modeled precisely. Black hole binaries reveal their presence through the motion of companion stars or X-ray emission from accretion disks. Both systems allow measurement of mass, spin, and distance, but only neutron stars provide evidence of a physical surface, magnetic field, and rotational pulsations. This dual method ensures observational clarity. You reflect on high-energy bursts and flares. Magnetars, a type of neutron star, emit bursts of X-rays and gamma rays when magnetic stresses rearrange the crust. These emissions provide information about the internal structure, magnetic field strength, and energy distribution. Black holes do not generate bursts intrinsically. Any high-energy emission arises from accretion processes. By analyzing the origin, timing, and energy spectrum of these signals, scientists can separate neutron stars from black holes, even when both are part of complex, high-energy environments. You notice how combining multiple signals enhances understanding. Electromagnetic observation, gravitational wave detection, and pulsar timing together provide complementary information. Thermal emission measures surface properties, pulsar timing tracks rotation and orbit, X-rays reveal accretion behavior, and gravitational waves reveal tidal interactions. The combination produces a comprehensive, evidence-based picture of each object. The differences between neutron stars and black holes emerge naturally, without speculation or ambiguity. You now reflect on the clarity provided by information flow. Neutron stars are luminous, pulsing, and structured. Black holes are defined by darkness and gravitational influence. Signals from light, timing, and waves allow observers to reconstruct mass, radius, rotation, magnetic field, and interior stiffness. Observational methods reinforce each other, producing a coherent, verifiable understanding. No object is mistaken for another when all available signals are considered. Finally, you rest in the calm understanding that the universe communicates clearly through light and gravitational waves. Each signal carries measurable, reliable information. Neutron stars reveal themselves with pulsations, thermal emission, and bursts, while black holes manifest through surrounding matter and space-time curvature. By following these messages, astronomers distinguish the two with confidence. As you breathe slowly, you sense that these signals are not only evidence, but guides, gentle, precise guides to understanding the fundamental nature of compact objects and the boundaries between them. You begin by allowing your mind to rest on the idea that even well-informed people sometimes confuse neutron stars with black holes. These misconceptions are not born of mystery or imagination. They arise naturally from the extreme properties of these objects. Both are incredibly dense, compact remnants of massive stars, and both emerge from similar stellar evolutionary processes. Because of these shared origins and extreme characteristics, it is understandable that casual descriptions or simplified explanations can blur the distinctions. Your focus is on understanding these sources of confusion and separating them with calm, factual clarity. One common misconception involves density and invisibility. Both neutron stars and black holes are extraordinarily dense compared to ordinary matter. To a distant observer, black holes appear invisible in the absence of accreting material, and neutron stars can be hard to detect if their beams do not intersect Earth. The result is that both objects may appear hidden, leading some to wonder whether a neutron star could secretly be a black hole. Observationally, however, the signals from neutron stars, pulsations, thermal emission, bursts are detectable and measurable. Their presence is confirmed through multiple independent channels, making the idea of disguise unnecessary. Another source of confusion comes from extreme mass and compactness. A neutron star packs more than a solar mass into a sphere roughly 10 to 14 kilometers wide, producing gravitational fields that dwarf anything familiar. Black holes, meanwhile, are even more compact, with masses exceeding the TOV limit. To those unfamiliar with the specific mass and radius ranges, the two objects can seem similar in scale. Yet astronomers distinguish them using precise measurements. The presence of a solid surface, pulsations, magnetic fields, and tidal interactions all confirm a neutron star, while black holes are recognized by their event horizon and gravitational influence alone. You notice how birth events contribute to misunderstanding. Both neutron stars and black holes originate from the collapse of massive stars during supernovae. Observing a supernova remnant can be confusing, because the core may collapse into either a neutron star or a black hole. Without follow-up observations, one cannot determine the outcome immediately. This temporal uncertainty can foster speculation. Yet over time, observations of pulsations, X-ray emission, or accretion signatures clarify the remnant's identity. Misconceptions arise not from lack of evidence, but from incomplete data at early stages. You reflect gently on simplified science communication. Popular accounts often describe neutron stars and black holes as exotic, almost mysterious objects, emphasizing density, gravity, or invisibility. While such simplifications make concepts accessible, they sometimes omit key distinctions, such as the presence of a surface or pulsar emissions. When repeated without context, these omissions can create the impression that neutron stars might be hidden black holes. By revisiting the underlying physics, mass, radius, magnetic field, rotation, and emissions, the distinctions become clear and misconceptions dissolve under careful scrutiny. Another factor involves magnetic fields and emissions. Neutron stars, especially magnetars, possess fields trillions of times stronger than Earth's. Their bursts and pulses can appear sudden and intense. Observers unfamiliar with these properties may associate the extreme behavior with black holes, imagining that they could produce similar signals. Observationally, this is not the case. Black holes do not emit directly from a surface. Any high-energy radiation comes from the accreting matter around them. Distinguishing between the source of emission clarifies the difference, and the extreme properties of neutron stars no longer imply disguise. You notice that gravitational wave discoveries also generate questions. Neutron star mergers and black hole mergers produce overlapping phenomena. Both generate ripples in spacetime detectable by LIGO and Virgo. To those unfamiliar with waveform analysis, the signals may appear similar. Yet the fine details, tidal deformation, post-merger ringdown, signal duration, allow scientists to differentiate between neutron stars and black holes. Misconceptions often arise before these analyses are understood or communicated, rather than from a failure of physics. The measurements are precise, repeatable, and provide definitive evidence once interpreted carefully. You reflect on mass thresholds. Some assume that any compact object is essentially a black hole if its mass is large. Yet observations show that neutron stars occupy a well-defined mass range below approximately 2 solar masses, while black holes start above 3 solar masses in observed systems. This clean separation allows astronomers to classify objects accurately. Misconceptions occur when these numerical boundaries are ignored or unknown. By anchoring your understanding in mass limits, the distinction becomes a matter of precise measurement rather than speculation. You gently consider surface versus horizon phenomena. Neutron stars emit pulses, bursts, and thermal radiation from a surface. Black holes, by contrast, have no surface. Light or matter that crosses the event horizon cannot return. The presence or absence of these emissions is a fundamental observational distinction. Misconceptions arise when people focus only on mass or density and ignore electromagnetic signals. Observational astronomy consistently confirms these differences, providing clear evidence that neutron stars and black holes are distinct classes of objects. You now examine rotation rates. Pulsars rotate hundreds of times per second, while black holes spin without producing periodic pulses detectable as signals from the event horizon. Rapid rotation in neutron stars produces regular, measurable timing patterns. Without understanding this difference, one might assume that fast-spinning objects are equivalent. Observations of pulsation intervals, spin-down rates, and changes in rotation provide robust evidence distinguishing neutron stars from black holes. Misconceptions disappear when these measurements are included in the picture. You reflect on how evidence from multiple channels resolves uncertainty. X-ray emission, radio pulses, gamma-ray bursts, gravitational waves, orbital dynamics, and tidal deformation together create a comprehensive profile for each compact object. No single property is relied upon alone. Instead, converging evidence builds certainty. Misconceptions often arise when partial information is considered in isolation. By observing the full range of properties, astronomers separate neutron stars and black holes with confidence, revealing the physics governing each object and dissolving any illusion of disguise. Finally, you rest in the calm realization that misconceptions are natural responses to extreme phenomena and limited exposure to data. Neutron stars and black holes are both extraordinary, but each behaves according to well-understood, measurable laws. The apparent similarities arise from overlapping origins, extreme density, and simplified descriptions, not from hidden or disguised behavior. By returning to the principles of mass, radius, rotation, magnetic fields, surface emissions, and gravitational interactions, the distinctions become unmistakable. You sense the quiet reassurance that careful observation and rigorous physics consistently reveal the truth about these compact remnants. You begin by directing your attention inward, toward the dense interior of a neutron star. Although the core remains inaccessible to direct observation, careful measurements allow you to infer its properties with confidence. Your mind rests on the idea that science provides tools to deduce what is happening inside, even without seeing it directly. Every conclusion comes from evidence, grounded in laboratory nuclear physics, astrophysical observations, and the laws of general relativity. The interior is a realm of extremes, yet your understanding is anchored in measurable reality. You start with the crust, the outermost layer of the neutron star. It is composed of atomic nuclei embedded in a degenerate electron sea. The crust is solid, supporting shear stresses that are responsible for phenomena such as pulsar glitches, sudden, tiny increases in rotation rate. Observations of these glitches provide indirect evidence of the crust's rigidity and its interactions with the superfluid interior. NICER and other X-ray telescopes detect changes in surface emission corresponding to these rotational shifts, confirming the predictions of theoretical models. The crust is a place where nuclear physics and astrophysics meet in observable ways. Deeper, you consider the inner crust, where nuclei coexist with a neutron superfluid. Neutrons in this region move freely, forming a superfluid that couples weakly to the crust. Pulsar timing measurements detect subtle shifts caused by the interaction of the superfluid with the rigid outer layers. These shifts match predictions from nuclear theory and superfluid dynamics, providing evidence that the superfluid exists without needing direct imaging. Your mind rests on the certainty that laboratory experiments with nuclear matter at lower densities inform models of the inner crust, connecting terrestrial physics to cosmic observations. You follow your attention inward to the outer core, where densities exceed those of atomic nuclei. The core is primarily neutrons, with a small fraction of protons and electrons to maintain charge balance. At these densities, the strong nuclear force dominates, producing pressures sufficient to resist gravitational collapse. Observations of neutron star masses and radii constrain how stiff or soft the core matter can be, as the equation of state determines the star's maximum mass. By combining X-ray, radio, and gravitational wave data, scientists place strict limits on the behavior of matter at these extreme densities. You now explore the possibility of exotic particles. Some theoretical models suggest that hyperons, mesons, or deconfined quarks may exist in the inner core. Yet even with these hypotheses, constraints from observed neutron star masses restrict their impact. Any proposed exotic matter must be consistent with the TOV limit and mass radius measurements. Observations of massive neutron stars, above 2 solar masses, rule out many exotic matter models that would overly soften the equation of state. Thus, inferences about the interior are always filtered through both theory and empirical evidence, ensuring that speculation does not override observation. You consider magnetic fields and rotation in the interior. The strongest magnetic fields observed in magnetars, up to 10 to the power of 15 Gauss, originate in the core and extend through the crust to the surface. Superfluid vortices in the interior align with the magnetic field and rotation, producing interactions that can influence rotational dynamics. Pulsar spin-down, glitches, and thermal emission provide indirect information about these interior properties. Every inference is grounded in observable phenomena and well-established physics, illustrating how interior conditions are connected to measurable behavior at the surface. You reflect on thermal properties. Neutron stars cool primarily through neutrino emission from the core and photon emission from the surface. Cooling rates are measured by X-ray observatories and are sensitive to the composition and state of matter in the interior. Models of neutron star cooling are tested against these observations, providing constraints on superfluidity, particle composition, and heat transport. Even without direct observation, the cooling history of a neutron star serves as a diagnostic tool, revealing internal physics with precision. You now examine tidal interactions in binaries. When neutron stars are in close orbits or merge, tidal forces distort their shapes. Gravitational wave measurements capture these deformations, providing indirect information about the star's internal stiffness. Softer matter deforms more, while stiffer matter resists tidal forces. These observations allow scientists to constrain the equation of state and confirm that the interior must behave consistently with nuclear physics. The signals are subtle but measurable, and they reinforce the reliability of inferences about matter at extreme density. You gently focus on limitations of current knowledge. There are aspects of the interior that remain uncertain. Precise composition at the deepest densities, the behavior of matter under extreme pressure, and the potential presence of exotic phases are still active research areas. Yet scientists remain careful, only proposing models that comply with observational evidence and physical laws. This discipline ensures that conclusions are safe, reliable, and scientifically grounded. Your mind rests easily, appreciating that uncertainty is acknowledged without undermining certainty where measurements are robust. You explore how different observations converge. Mass and radius from X-ray timing, gravitational wave tidal deformability, pulsar spin-down rates, and magnetar flares all inform interior models. Laboratory nuclear experiments provide complementary constraints on how matter behaves at high densities. By synthesizing these independent lines of evidence, astrophysicists construct models that match reality as closely as possible. This convergence provides reassurance. Even without direct imaging, the internal structure of neutron stars is inferred in a controlled, evidence-based manner. You consider the connection to the TOV limit. The maximum mass supported by neutron degeneracy and nuclear forces defines whether a neutron star remains stable or collapses. Observationally, no neutron star has been found above approximately 2 solar masses. If the mass exceeds this, collapse into a black hole occurs. This boundary emerges directly from interior physics and serves as a measurable, reliable criterion for distinguishing neutron stars from black holes. Your mind appreciates that even unseen interiors obey exact physical laws. You reflect on responsible scientific inference. It is important to separate what can be inferred from what cannot. Observational data allow conclusions about density, pressure, composition ranges, and stiffness. They cannot reveal every microscopic detail, but they constrain possibilities tightly. By respecting these limits, scientists maintain accuracy and avoid speculation. This careful approach illustrates how knowledge grows steadily, each measurement adding clarity while remaining consistent with established physics. Finally, you rest in the calm understanding that the interior of a neutron star, though unseen, is a well-mapped domain of extreme matter. Crust, core, superfluid, magnetic field, and thermal properties are inferred with precision from multiple complementary observations and grounded in laboratory physics. The boundaries between what is known and what is uncertain are clearly recognized, creating a stable, reliable picture of these dense remnants. You sense a quiet certainty. Neutron stars are defined by measurable physics from surface to core, and no conjecture can erase the careful evidence that guides our understanding of their hidden interiors. You begin by letting your mind return to the original question, now seen with the clarity of all you have explored. Neutron stars and black holes, while both extraordinary, are fundamentally different objects governed by well-established physics. Every distinction is measurable, observable, and consistent with theoretical models. Your thoughts settle on the calm certainty that the universe communicates clearly through light, gravity, and matter, and that no hidden deception exists between these two compact remnants. You review the mass and radius distinctions first. Neutron stars typically range between about 1.1 and 2.0 solar masses, contained within a sphere roughly 10 to 14 kilometers across. Black holes, as observed in astrophysical systems, generally begin at about 3 solar masses and have no measurable surface radius, only an event horizon determined by the Schwarzschild formula. These ranges do not overlap significantly. Observational evidence, including pulsar timing, gravitational wave measurements, and X-ray spectroscopy, confirms these limits. The numerical boundary alone prevents a neutron star from masquerading as a black hole. You focus next on observable surface phenomena. Neutron stars have solid surfaces and emit detectable radiation from their crusts. Pulsars, with their regular beams of radio waves, and magnetars, with bursts of X-rays and gamma rays, provide unmistakable evidence of a physical object with a surface and a magnetic field. Black holes, in contrast, produce no such direct emission from within the event horizon. Any observed radiation originates from surrounding material, not the black hole itself. The presence or absence of a surface signal provides a clear observational criterion that distinguishes neutron stars from black holes in any system. You reflect on magnetic field differences. Neutron stars possess extremely strong magnetic fields, reaching up to 10 to the power of 15 Gauss in magnetars. These fields shape pulsar emission, influence crust dynamics, and produce measurable effects on surrounding plasma. Black holes have no intrinsic magnetic field, though they can interact with fields in the accretion disk or jets. Observations of surface magnetic activity, pulsar spin-down, and high-energy bursts reinforce that the presence of such fields is unique to neutron stars. The difference spans many orders of magnitude, creating a fundamental distinction that cannot be bridged. You consider rotational behavior. Neutron stars rotate rapidly, with periods from milliseconds to a few seconds. This rotation produces periodic pulsations detectable across radio, optical, X-ray, and gamma-ray bands. Black holes also spin, but without a physical surface, there is no mechanism to produce periodic emissions tied to the spin. Gravitational wave observations of mergers allow measurement of spin, but again, no pulsations originate from within the horizon. Observing a periodic signal immediately indicates a neutron star, confirming that spin characteristics reinforce the distinction between these objects. You explore tidal deformability and mergers. Gravitational wave measurements from neutron star mergers reveal how the stars deform under each other's gravity. These deformations depend on internal structure, stiffness, and composition, all measurable through the tidal response. Black holes, having no material surface, do not exhibit tidal bulges. The gravitational wave signatures therefore differ distinctly, allowing precise identification of each object in a merging system. The physics is consistent, observable, and repeatable, leaving no ambiguity between neutron stars and black holes. You now turn to the equation of state and internal physics. Neutron stars are governed by nuclear interactions and degeneracy pressure that define their structure and maximum mass. Black holes, beyond the event horizon, have no such internal pressure or structure. Exceeding the TOV limit transforms a neutron star into a black hole, but until that point, the physics within the star is distinct, predictable, and measurable. NICER, Chandra, LIGO, and other observatories provide data that directly inform the equation of state, confirming that neutron stars remain solid, dense objects until collapse occurs. You gently reflect on collapse pathways. Accretion from a companion, binary mergers, or extreme progenitor mass can push a neutron star beyond its limit. Observations of post-merger gravitational waves, sudden disappearance of pulsations, or accretion-induced collapse confirm that the transition to a black hole occurs when the TOV limit is exceeded. There is no reversal, no hidden mechanism, and no disguise involved. The universe operates consistently, and each pathway is documented and predictable. Neutron stars may become black holes, but they do so in full compliance with established physics. You notice how light and timing signals consolidate the picture. Pulsar beams, thermal emission, X-ray bursts, and gravitational waves all communicate measurable information about neutron stars. Black holes communicate only through the effects on surrounding matter and spacetime curvature. By analyzing the full spectrum of signals, astronomers distinguish objects with certainty. There is no overlap that suggests one object could be masquerading as the other. Each method confirms and reinforces the other, producing a coherent understanding based entirely on observational evidence. You consider common misconceptions one final time. Confusion arises from shared origins, extreme density, or incomplete descriptions, but careful measurement resolves each point. The physics of neutron degeneracy, magnetic fields, rotation, and mass thresholds ensure that each object has a distinct, measurable identity. Pulsar timing, gravitational wave analysis, and X-ray spectroscopy provide repeated confirmation. There is no need to speculate about hidden identities, because each neutron star communicates its nature through a wealth of independent signals. You reflect on the importance of evidence-based reasoning. Every inference about neutron stars, their interiors, and their limits is grounded in measurable data. Mass, radius, rotation, magnetic field, tidal deformability, and thermal emission collectively define the properties of neutron stars. These properties are consistent with nuclear physics, general relativity, and laboratory experiments. Black holes, governed by different criteria, occupy a separate domain. The distinction is clear, reliable, and supported by decades of observations. Your understanding rests on solid, verifiable foundations. You notice how the combination of techniques, radio, X-ray, gravitational waves, timing, and spectroscopy, provides redundancy and precision. No single observation is relied upon in isolation. Together, these measurements paint a complete picture of each object's identity, confirming both the presence of neutron stars and the criteria that define black holes. Science provides a calm assurance that the universe is comprehensible, even under extreme conditions, and that observational evidence is sufficient to remove doubt or confusion. You reflect on the quiet consistency of the cosmos. Neutron stars exist as dense, solid, highly magnetic remnants, and black holes exist as regions of spacetime from which nothing escapes. Each obeys its own physical rules. Observations confirm these behaviors repeatedly in systems nearby and across distant galaxies. There is no hidden masquerade. The universe communicates honestly through measurable signals. By listening carefully to these messages, your mind rests with confidence in the clarity of physical law and the predictability of extreme matter. Finally, you rest in the calm understanding that neutron stars are fully themselves without disguise. Mass limits, surface emissions, magnetic fields, rotation, tidal responses, and gravitational wave signatures collectively define their identity. Black holes are distinct, defined by mass and the event horizon, and their behavior confirms the absence of a surface or internal structure. Evidence guides every distinction, and repeated observation confirms the science. As your mind lingers on this certainty, you sense a gentle curiosity about future observations, refinements in measurement, and the evolving precision of astrophysics. The universe, in its extremes, continues to communicate with clarity, offering rest in both understanding and wonder.